Good evening and thank you for watching this presentation on behalf of Assignment Group 18. In this assignment we'll be investigating variables impacting takeoff. Firstly, in Task 1, the group investigates the minimum thrust needed for an aircraft to take off. Secondly, in Task 2, the group investigates how the inhibited thrust allowance determined in Task 1 affects aircraft performance when in high altitude and density. The investigatory assignment uses the Griffith University Flight Lab simulators with a CRJ-200 jet aircraft to record the data and ensure consistency between variables. Within Task 1, Group 18 investigated the minimum thrust required for an aircraft to successfully and safely take off at Brisbane International Airport on runway 01 left whilst at the maximum takeoff weight of 24,040 kilos. It is important to note that the total reusable runway length is 3,300 metres as per the AIP chart of YBBN. The data was recorded by using the Flight Lab simulators and decreasing the maximum available thrust of the CRJ-200 in 10% increments until the minimum thrust needed for the aircraft to take off was determined. Quick visualization of a typical test can be seen on the screen now. In order to determine the thrust output used for each takeoff was appropriate, the distance that it took from brakes release to liftoff was determined. If the distance from brakes release to liftoff was longer than the available runway, then the thrust level used for that test was insufficient and can be classed as a failure. This was done using data from the X-plane output and placing it into an Excel spreadsheet. From there, the latitude and longitude coordinates at the beginning of the takeoff were recorded, and the coordinates at the end were recorded as well. These were then placed into a latitude-longitude distance calculator to find the total takeoff distance for each trial. Each thrust level and its distance can be seen on the table shown on the screen. The rotation speed for each trial was calculated at 1.2 VS using a stall speed of 130 knots. Therefore, the liftoff speed VLO was 156 knots for each trial. It can be seen from this data that the 56% reduced thrust trial utilised 4,057 pounds of thrust and was able to successfully take off with a distance of 3,152 metres. However, the 58% reduced thrust utilised 3,978 pounds of thrust and was unable to take off in the available runway distance of 3,300 metres. This data can be seen here in Table 2. Therefore, the minimum thrust required for a successful takeoff at YBBM is assumed to be 57% decrease in thrust, utilising the entire usable runway length of 3,300 metres. Here are two videos side by side of the 50 and 60% reduced thrust takeoffs. However, utilising the equation shown in this slide, the minimum thrust for a takeoff where the distance of the runway is 3,300 metres by Air Services Australia and the aircraft has a weight of 24,040 kilos could be calculated. Please note that while in the assignment task sheet it does state that the runway length of 01 left is 3,505 metres, consulting the AIP aerodrome chart from Air Services Australia, the actual usable runway length for this runway is only 3,300 metres. This latter distance will be used in our calculations. Rearranging the equation to solve for T provided a minimum thrust for takeoff at any airport as 5,374 pounds. This value is significantly higher than the minimum that was actually used in the simulator. This is due to the fact that the equation does not account for factors like friction and drag, however the simulation does. Similarly, the equation utilised thrust required, although the simulation trials were operating off of thrust available, which may be another reason the two values are so vastly different. The calculation shown is for thrust required instead of thrust available. The calculated minimum thrust from the equation sits between 40% and 50% reduced thrust values tested in the simulator. The distance, however, does not. Instead, the data from the simulation shows that using linear interpolation, takeoff distance for the calculated minimum thrust should actually be approximately 2,300 metres. A visualisation of the calculated minimum fits within the simulation data can be seen here on this table. The minimums calculated mathematically versus the minimums found in the simulation show that the mathematical method does not fully capture the variables that affect the minimum thrust required, such as drag and the effect of friction. Therefore, the calculated minimum number for this is higher than what was tested in the simulator. The calculated minimum thrust required using the equation in the value that will be used in task 2. However, the answer to task 1 still needs to be determined in its entirety. So, utilising the equation on the slide here, the time to take off at minimum thrust at YBBN runway 01 left can be found. An important note to make is that the TSL over W is calculating the thrust to weight ratio of the aircraft. Specifically in this case, the thrust of the aircraft is with regards to the thrust at sea level, which is stated in the engine specs as 9,220 pounds of thrust. The weight in this instance is at max takeoff weight, which is 53,000 pounds from the Bombardier Incorporated manual. Therefore, the answer to the task 1 is 57% reduced thrust at 3,900 pounds, utilising the entire runway length of 3,300 metres with a takeoff time of 47 seconds. It should be mentioned that although the original full-power takeoff clearly had a quicker rotation time and used less runway, using the TR would be considered significantly safer due to the added control over the aircraft in this case, in case of an engine failure or emergency. More drag is also produced in this scenario due to a lack of lift. The aim of task 2 is to attempt a takeoff in the CRJ 200 at the calculated minimum thrust found in task 1 at an airport with a much higher altitude than YBBN. The main goal of this task is to observe and analyse how air density and altitude affect takeoff performance. The second part of this task is to then make an aerodynamic change to the aircraft if the initial takeoff fails. The purpose of this is to observe what needs to be done in order to have a successfully reduced thrust takeoff at a high altitude. Similarly to task 1, the CRJ 200 will be attempting takeoff at its MTOW 24,040 kilograms. The airport used for this trial is Cusco Airport in Peru. It was chosen as it has an elevation of 10,860 feet above sea level, and in standard conditions this means that it has a density altitude of 13,000 feet. The maximum thrust available to the CRJ 200 in this task is 5,374 pounds as per the findings in task 1. The initial takeoff was performed at the MTOW in a clean configuration, and as suspected, the takeoff was unsuccessful. The aircraft was unable to gain enough airspeed to successfully rotate before the end of the runway. The second trial, however, changed the variable of adding full flaps 45 degrees to the CRJ 200. After attempting to take off again in this new configuration, the aircraft successfully took off before the minimum runway lengths. You can see in this comparison here of the two trials on the screen now. The recording on the left is the clean configuration takeoff, and the recording on the right is the change configuration with added full flaps. As you can see, both aircraft are quite sluggish. Due to the minimum amount of thrust being used, as well as the full flap variable being added, a new stall speed for this configuration at this airport can now be calculated from the data that X-plane outputs. As you can see here on the slide, the calculations are explained. Because of the correct stall speed for this configuration having been calculated, a new liftoff velocity can also be found. The distance that was achieved for this successful takeoff was also calculated using the same method as Task 1 and was found to be 3,062 metres, where the full available runway distance at SPZO Cusco Airport is 3,400 metres. On the first unsuccessful takeoff attempt, the aircraft did in fact achieve the new VLO speed. However, due to the air density and elevation of the airport and lack of lift being generated from the surface area of the wings, the aircraft could not take off. Similarly, on the second attempt, the aircraft also achieved the new VLO speed, however only due to the change in flaps did the aircraft take off. It is known that when at a higher altitude airport, more thrust may be needed to be used for a takeoff due to this change in air density, specifically when using an aircraft like the CRJ-200, which houses a turbofan engine. The decreased air density at a higher altitude affects the engine by the lack of air being supplied to the engine, causing less thrust to be produced as the aircraft weight becomes too much for the engine or engines to carry. To maximise the thrust output in higher altitudes with a lower air density, the engine must work harder in order to control the high RPM output. The reason that the first takeoff attempt in this clean configuration did not work is because of that. Due to the lack of thrust from the turbofan engine in a higher altitude and lesser air density, the engine simply did not have enough power to lift the MTOW of the CRJ-200 without aiding factors such as increased lift production. Once the aerodynamic capability of the wings was increased by adding flaps to the second attempt, it succeeded because of the surface area of the wings being increased from the clean configuration, allowing for more lift to be generated, compensating for the opposite force of weight, allowing for a successful takeoff. However, the downside of adding more flaps means that the induced drag increased, which provided an explanation as to why the aircraft accelerated much slower than the clean configuration trial. It should also be noted that the higher altitude takeoffs use significantly more runway compared to the YBBN takeoffs. This too is due to the facts of lift and thrust. Throughout this assignment, the group has investigated the effects of reduced thrust takeoffs. It has been found that in circumstances where the aircraft is in fact having enough air to the engine or can use flaps to aid the takeoff, a reduced thrust takeoff may be useful, as it provides more control over the aircraft. A real-life example of this is in a 2023 ATSB report where 2 aircraft from Melbourne Airport decided to perform reduced thrust takeoffs, which would have been suitable for a full-length runway and the air density altitude. However, the northern end of the runway was shortened due to resurfacing works from 3,657 metres to just 1,568 metres with poor communication belt works. Unfortunately, these causing runway excursions, damaging temporary runway lights and partial works. Clearly, as this was a low-level airport, a reduced thrust takeoff would have been more than appropriate and safer due to the overall control of the aircraft. Overall, it can be found throughout this assessment item that the aerodynamic forces such as thrust also depend on their counterforces such as weight, lift and drag. If not enough thrust is produced in an engine during takeoff, the lift is accelerated, causing a longer runway lengths to be used and the takeoff time to slow. By increasing the power generated, a takeoff can be quicker in time and less runway to be used. When introducing flaps, the surface area of the wings is increased, creating a larger area of the aircraft to generate lift. Higher altitudes and low density air can affect the aircraft's performance significantly when these forces are in play. And that concludes this presentation. On behalf of Assignment Group 18, we would like to thank you for your time.